All right, still doing good, or you need a quick break? All right, we're going. Okay. All right, we'll finish off class today. Finish off some aerodynamics, and then we got a couple of charts to talk about. So load factor. The load on the wing is what we're talking about. Any force that deflects the airplane from a straight line is going to produce a stress on the airframe. You've probably felt that if you've done a rapid nose pitch up, you've felt a little bit of oomph on you. Or even in a steep turn, if you've pulled back a little too aggressively, you felt yourself being pushed into the seat. You know, your airframe's going through a stress point as well. So that load factor comes in to the equation here of, well, how much lift are you producing? And that's set over the gross weight, so lift over weight. In normal flight, level flight that is, wings level, straight flight, you are producing 1 unit of lift, or say 3,000 pounds of lift for your 3,000 pound airplane. So 3,000 pounds of lift over 3,000 pounds of airplane, that's a 1-to-1 ratio. So you're pulling 1 G at that point. When you roll into a level turn, we know that we roll, we coordinate with the rudder, but we also pull on the yoke. We know that the amount of lift developed, lift is always measured in a perpendicular fashion to the wing. But weight still remains in this vertical plane. So we need a vertical component of lift that's equal to the weight of the aircraft. So we're pulling on the yoke to increase our total lift so that the vector of vertical lift is equal to the weight of the aircraft. Since we're pulling more total lift, but our weight hasn't changed on the aircraft, the load factor has now increased. Make sure we understand this concept here. Let's take a moment for a question here on Top Hat. Okay. We got 2 questions here. First one, you're in the normal flight region. Think about that power curve. You're in that normal flight region where if you add power, you go faster. Okay? What is the proper way for a pilot to increase lift in order to maintain level flight with a 30-degree bank angle? So there's your question there. Don't think too much into this question here. We're just talking about lift. It should be an easy one. We've ingrained this in you since day 1 of your flying. All right, I'm very surprised. This should have been 100%. You're out there, you roll into a turn, you're losing altitude. We've taught you to pull back on the yoke. Okay? 11 of you said increase power. So are 11 of you saying I'm going to roll to 30-degree bank and rolling up the power to maintain level flight? I don't think so. Right? I think you go out there and you roll, you pull. Because that's what we taught from day 1 there. All right, so if you're one of the 11 there, all right, go back to some aerodynamic principles here. All right, I got another question though. This time, I'm going to put you in the slow flight region. You're on the backside of the power curve. Remember, you know you're on the backside of the power curve when, if you want to fly slower, you have to add power. But the question is, the proper way for a pilot to increase lift in order to maintain level flight with a 30-degree bank angle. Again, don't overthink the question here. We're talking about lift development. All right. Here we go. How'd you respond? Oh. What? Whoa. Talking about lift development. Okay. Let's go back. Let's go back to this slide right here. Whenever you roll an airplane, we need more total lift. And the only way you're going to get total lift, oh, I'm sorry, there are two ways, right? The proper way for you to get more lift is to increase the angle of attack of the aircraft. By increasing the angle of attack, you get more total lift, and so the vector of vertical lift is then equal to the weight of the aircraft. That is how you do it. So why did 41 of you say increase throttle? Go ahead, Henry.
Because when you're in slow flights, if you increase the power, then you increase the airflow.
This is true. You are absolutely correct on that. But herein lies one problem for the commercial pilot. You've got 5 knots to play with on your check ride. And when you go up with me, we're going to do slow flight. We're going to do 30-degree bank angle. And if you try to increase your speed only to maintain level flight, you are going to exceed that 5-knot tolerance. Oh, wow. Now, I didn't ask this question, but a lot of you think, if I'm in slow flight, I better pitch down and increase power. And if you're thinking that, why would destroying lift be the answer to maintaining level flight? Because then you have to add so much more power just to maintain it, get that lift back that you need. We increase the lift, but we know in slow flight, we increase drag too. So we do have to increase the throttle to overcome the drag that you created. But you have to increase angle of attack. It doesn't matter how fast or slow you're flying the aircraft. I am surprised because usually everybody answers it incorrectly, but 10 of you answered it correctly, so good job. All right, let's look at this a little bit more. How much G's are we pulling on an aircraft? And so if we have our 3,000-pound aircraft, the 0-degree bank angle, we're pulling enough lift for 3,000 pounds of airplane. So a 1-to-1 ratio, that's 1 G. Now we do have charts that can help us understand how many G's we're pulling, but in a 30-degree bank angle, when I'm in level flight, that equates to 1.3 times the force of gravity. So I'm pulling, it's as if I have, I guess the effectiveness on the airplane is just like it's 3,900 pounds. It's not, it's still at 3,000, but you've added an extra 900 pounds of lift to it. So now you're pulling 1.3 Gs. When you get into a 60-degree bank angle, and that's the one you should know as a pilot, you are pulling twice the amount of lift on that just for level flight. So your 3,000-pound airplane feels like it's at 6,000 pounds. You feel like you're double your weight. And if you didn't have an armrest, if your hands were floating on controls freely, you would feel your arm being pulled down on it. As it is, you're probably feeling like you're pushed into your seat. So how much is too much? How much lift is too much lift before the airplane starts to fail or become damaged? Right? So for a normal category aircraft, which is your Cirrus SR-20, the regulations state that it must withstand a minimum of 3.8 Gs before damage occurs. Because that's positive, and the negative amount is 1.5 Gs. So that means all the way up to 3.8 positive or negative 1.5 Gs before damage occurs. Now, it would really be a bad day if you went to 3.9 Gs and the wings broke off of your airplane. So the FAA put in a little bit of a safety factor, a margin of 50% above those limits, which means that your 3.8 Gs plus the 50% safety margin means the wing has to be able to withstand 5.7 Gs without failing. Now, once we're past 3.8 Gs, it will be damaged, but it won't fail because it has to withstand up to 5.7 Gs. And very similar stands with the negative, it has to go to negative 2.25 Gs without failing. So this means we're very dependent upon knowing what the load factor is for our certain phase of flight and understanding that there's a relationship between our speed and how many Gs that we can pull on the airframe. And we're going to start taking a peek at what we call the VG diagram, the velocity G-force diagram. And that's constructed with the concept here that the stall speed increases by the square root of the load factor. You know, load factor of 1, let's see, square root of 1 is 1. We have no change in stall speed. If I pull 2 Gs, square root of 2 times 60 means my airspeed for stalling increases from 60 to 84.8. So the more Gs I pull, the greater the stall speed becomes by a factor of the square root of that load factor. So let's try a top hat question. You'll need a calculating device. We're looking at a load factor of 1.5 Gs. What is the stall speed for the Cirrus SR-20 with the VS1 of 65 knots? So somewhere around 79.5 would be the correct answer there. So square root of 1.5 times 65 is how we're answering that problem there. And then just add it back on to the speed. Okay. Try that again at 2.5 Gs. What is the new stall speed for the aircraft? So square root of 2.5 times 65, and then add that on. It looks like most of you got that one right, somewhere around 103 knots now. So this is our VG diagram, velocity G-force diagram. It really makes up the envelope of the aircraft. We want to make sure that we understand how it's constructed. Your assignment E1 is going to be developing a VG diagram for the Cirrus SR20. Starting here at the 0 point, which is 0 Gs. This line here that curves upward is the maximum lift that that wing is capable of developing at that speed. Okay. So when we're below certain speeds, we can't develop very much lift before the airplane stalls. Once we're going fast enough, then we have the ability to develop so much lift that the aircraft could be structurally damaged. And similar feat with the negative line here. And of course, this positive limit here is based upon the square root of the load factor times the stall speed. And so we're really looking at this concept here that if an aircraft is at 75 knots, it can pull about 2.1 Gs. Beyond 2.1 Gs, it just stalls. There's not enough speed for the amount of G-force being developed. So it's you in level flight, you pull back so much on the yoke that you exceed 2.1 Gs, you just stall. Looking at an aircraft, and for the most part, your graph that you designed will look like this. Right? We overlay the airspeeds from the airspeed indicator on here. Okay? Make a note, VS1 occurs at 1 G. Everything's based upon VS1 at 1 G. So that is a given right there. The next point, you have to understand where the load limit factor, which is 3.8 Gs, meets that curved line, which is how much lift that wing can develop. That is your maneuvering speed. Here it's labeled VA, and you're probably thinking, well, in my Cirrus aircraft, it's called VO. Small differences between the two, but effectively we're looking at a speed at which we can exercise a control surface to its maximum deflection without damaging the aircraft. So that's why when it is bumpy out, we fly no faster than VA speed so that we are in the stall region if we exceed G limits. Because if you're faster than maneuvering speed, and you exceed 3.8 Gs, you're in structural damage region. And of course, we can look at the last portion of this envelope here as your never exceed speed. And from there, we just color code the white arc. Notice how it overlaps in the green arc. And then we have the green arc up until it meets the yellow arc. So effectively, you're going to design something that looks very similar to this. You're going to be overlaying different speeds on it as part of the assignment. Questions? Let's see if you have anything written down here. Okay. How quickly can a large turbine engine go from idle power setting to producing cruise thrust in flight? I don't know. Not an expert on the turbine engine. Our turbocharged engine from idle to full power was usually about 6 seconds in our Piper Seneca that we flew. Other than that, I don't know. Well, I don't have much more. Just a few more slides, a few more top hat interactions.